Recording. Yes. All right. So today I'm streaming to Facebook Live instead of YouTube. I have a feeling that I'll be able that, I don't know, the connection might be a little better. Better? I might reach more people on Facebook Live. I'm not sure. Realistically, I'm probably going to end up streaming to both eventually. We'll see. But what I'm going to do is I'm going to record this and then stick it on the YouTube as a video instead of a live stream. Because the video itself does actually catch more viewers than the live stream does. I really need to balance this bench. Okay, what are we doing? I got some stuff going on over here. Well, I'm going to put my phone up over here so I can watch the... Can I see the comments? I got to figure out how to see the comments. Does this give me a comment stream? Yep. Hey, Nick. How's it going? So my comment stream is over here. So if I am, if I'm off the camera a little bit, then I'm probably trying to see the comments. Tilt my screen a little bit that way. It'll be easier to see. All right. Now, got a bunch of stuff going on. I did a couple things off camera because I wanted to try and prepare. Even though the entire point of the live stream is all the preparation is on camera, I don't know, I was nervous about it, so I'm like, let's do a little preparation. So I made another power box. I'm actually kind of liking this. I'm going to end up with too many of them. This is not the same one. It's a second one. So this is only 1 amp, and this here power box is 5 amps. So there's a 5 amp circuit breaker in here. It is plugged into 110 volts, because that's how we do. Just wait till I get 220 volts, because that's what they do in Europe. Okay. Let me know if you guys can hear okay. Let me know how it sounds. All that kind of wonderful happy horse shit. All right. So the entire point of today's, the first experiment we're doing today. This is a coffee pot warmer. Pretty obviously. It's off of a commercial Bunn coffee maker, and it's not complicated. It's just one coil under here. So what I have is I have my 110 volt going to one lead. I'm using the multimeter to test the amperage. Oh. I'm watching the video and I got captions on. It confused me because apparently I'm easy to confuse. So this really is actually a quite simple operation. I have a switch and a circuit breaker here for safety purposes. Anything over 5 amps and it'll trip the circuit breaker. I have the multimeter set in series. That means it's in the loop for measuring current. Putting the amp clamps work well, but it is more accurate to actually have your meter in series because the meter has what's called a current shunt inside and it can measure the voltage drop. It's a more accurate way to do it. All right, so I have 110 volts going to the red lead, to the meter, back to the element on the bottom here, and then to neutral. Fairly straightforward arrangement. Now what I'm going to do is I'm going to turn this on. I measured the resistance earlier at like 144 ohms. So at 144 ohms, we're doing less than 1 amp, which seems a bit odd for producing the heat. Let's see the wattage. Less than 1 amp at 100. So we're doing less than 100 watts. Less than 120 watts. I don't know. Maybe we'll do the math to it, but that doesn't seem like much, but I guess we'll see. If this turns out to be kind of not worth it, I have another one. Another heater over here that I actually pulled out of. It's a crankcase heater out of an air conditioner, so maybe that one will work. But that one's designed for 220 volts, so I don't know. We'll see again. Let's do this. All right, so set the meter to amperage. Right? Turn it on. All right, we got 0.8 amps. Oh, I forgot to mention, the other thing I got is this here thermal imager, so that we can take the temperature. So at 0.8 amps, okay, let me check the camera. There you go. And there. We can see something happening. It's genuinely not a lot, though. It really isn't. I'm trying to... Sorry. I know it's goofy. This is like trying to aim using a camera. So you can see it warming up there. It's not doing too bad. Let's see if I can get a temperature. All right, what's my temperature? 149 degrees. Hey, that's pretty good. 161 degrees. Is it really? Yeah, it is. At 0.8 amps. Now, 170. All right. Let's do the math on that. Calculator. Hold on. Calculator's right here. All right. Math. Math time. Wattage calculations and wattage calculations are actually pretty darn easy. All we got to do is multiply the voltage, which is 120 RMS. We're just going to go with that number, times 0.82 amps. It's 98 watts. It really doesn't seem like a lot. In fact, I'm going to say in the realm of coffee making, that's really not a lot. Yeah, that's really not. Maybe I'll plug the other one in and see what that does. Yeah, so it looks like its temperature range is... Oh, now we're up in the 260 range. But here's the thing. With that kind of wattage, I'm actually going to turn this off now. With with less than 100 watts, that's not even 1 BTU. No, wait, yeah, it is. 1 BTU is 76 watts, I think. I could be wrong. I don't have my phone on me to double check, but that's not much energy. Not gonna lie. I was kind of hoping that would be more. And the reason I was hoping that would be more is because I need this to like actually heat up whatever thing is sitting on it. Well, whatever thing, the coffee pot, right? So what I was hoping to do, what I was hoping to do is use the coffee pot to act as the boiler itself. And I was going to modify the top to, you know, put a little insert in the top and have like a thing. But I'm not super confident that's going to work now. I have to figure this out. So let's see. If I'm pulling a vacuum on water, I need to figure out how many BTUs I can pull out of water at a certain vacuum. Without doing a bunch of more math, this honestly is probably going to be... We're going to go with it. We're going to go for it. Let's take this down. I'm going to take this down and rebuild this with our other heater and see what that does. Yeah. Ooh, that's hot. It's hot. Ha! It's hot. Don't fucking pick it up like that. I'm a genius. Okay, so the other heater I have is this here compressor crankcase heater. Now this compressor crankcase heater is designed for 220 volts. So it's not the same. Now the first thing I'm going to do is I'm going to check the resistance of this element, and I can use that to determine roughly what current it will draw. Do. Come on, man. Why you gotta be difficult like that? Uh, Holy smokes, that's 2,000 ohms. We're not gonna do piss for amperage on that. I mean, I could do the math easy enough. So if I take 120 divided by 2,000, that's 0.06 amps. That is significantly less. That's kind of unfortunate. If I wanted to raise the energy output, I would need to parallel. I wonder if I could do that. No, there's really not much room in there, not unless I could stick another element under it. I don't know. Getting a little worried about that. But we'll see. Okay. So I want to clamp the one. All right, so we're going to clamp that one. And this one, I'm going to do some redneck stuff. All right. Ready for it? Let's see what it does. What did I say? 0.06 amps? 0.05 amps. Yeah, that is not much. And honestly, that would take a while for the heat to actually do anything on that. Yeah, that's not much. All right. So I have, either way, you can kind of see. Now, why am I doing this? Because I want to know the amperage that this circuit is dealing with, that I'm dealing with in this circuit, because I need to size my components accordingly. And with less than 1 amp, I can easily use my smallest components, cheapest components, to accomplish the goal. And the goal is the SCR driver that we're going to use for automatic temperature control. Dude, the thing we tried to design the other night that didn't quite work. Oh great, now I got a tangle. Ta-da! Alright, I'm going to set this on my bottomless pit bench. We're going to unplug this here power supply. I need to label these. I need to get my label maker out, and I need to label these. Yeah, 5 amp and 5 amp and 1 amp. What did I do with the other one? Sure, it's down here somewhere. Okay, now to the result. So I have some components here. One, I need an opto isolator, MOC. There we go. MOC 3021. Bing pop. And now, hey, that actually works out kind of nice, having that set up like that. These are switches. These can go over here. And is this it? Yes, BTA. All right, so BTA 08. BTA 08 is my triac. All right. This circuit is honestly very simple. So I'm thinking I may just go with a breadboard to perform this operation in testing. We'll use the breadboard. We'll save the soldering. This works. It's great. We love it. But we're going to save the soldering for, which breadboard do I want to use? I'll do this one. Now, I am going to need to reprogram these things. Okay, breadboard. Breadboard's a bit of a mess. We're going to demessify it here, quick. Let me get my Arduino out of here. Display. This is the display I'm using? Yes. This is the display I'm going to end up using. All right. So what this is, in case you're not familiar, a breadboard. Breadboard is this little gadget that has all these tiny little holes in it. And the way this works, and I'm only saying this for anybody that doesn't already know, the way this works. Ooh, I got some fiberglass dust. I cut my PCB, and it turns out that's fiberglass, and it made some dust. All right, so for anybody that isn't familiar with breadboards, the way this works is we have multiple rails, and these holes here are specifically designed so you can take, components and push them in like that, like so. It allows you to put things in, and then you use these here wires to make. And what you have is you have two rails on each side, denoted as positive and negative. You can swap it how you want, but it's one common rail going all the way down this way and all the way down this way on each side. Two here, two here. That's your positive and negative rails. In this case, I have a little mini power supply over here that powers those two rails automatically for me. Automatically. And then these slots go perpendicular. So I have, for each line, and they're actually numbered, but for each line, I have two sets of rails. But it allows me to do things like I can plug this here triac over here, and then I can plug a wire here, and now that wire is connected to the one pin of the triac. That's a breadboard. That's what we're doing. It's nice and convenient that way. Now I need to think about the actual circuit design that we're using, and I also need to pull up the pinouts for these circuits. Yes, I do. And I neglected to... Oh, good audio and video. Thanks, Nick. Fantastic. So I completely neglected to... I guess I'll use my phone. Bring up this information ahead of time. Going to clear some things out. All right, so when you're designing with electronic circuits, one of the first things that you should be doing is researching the pinouts and the data sheets for the circuits that you're using. So MOC 3021, MOC 3021 data sheet. Okay, because of course I did not spell data sheet correctly. Let's see if DigiKey has a data sheet on it. Everything's got a cookie. Here we go, data sheet. There we go. Can you see that? Well, sort of. Hey, Rupa, if you're listening, could you bring up my iPad that's in my lunchbox, please? Okay, so I know you can't see this terribly clearly, but what I'm looking at is the data sheet for the MOC 3021. Now, the pinout, pin 1 on an IC is always top left. I make that statement. I may not be able to, that may not be 100% correct. So I guess don't listen to me. Don't put all your eggs in my basket. All right, but what I do know from this data sheet is that I care about pins 1 and 2, which is 1 and 2, and then pins 6 and 4. So the pins go 1, 2, 3, 4, 5, 6. So when I put this on here, I'm going to put it like this. I'm just going to put it over here just for the sakes of putting it over here. All right. And I put it in there. Now, conveniently, these little circuit chips fit nicely in that center piece on the breadboard. They design it that way. It's almost like they mean that on purpose. Now, I'm going to take And I'm going to take pin 1, and, well, let's see. I want to use an output from this here Arduino Nano, and I'm going to go with digital output 2, I guess. Well, digital output 1 is right there. I'm going to digital output 2. Is that what I want to do? Maybe not, because I might be using an 80 tiny in this. Not 100% sure. All right, and then I'm going to take, I need a 220 ohm resistor. Yes. All right, I need to take the resistor, and I'm going to take this, and I'm going to send it to ground. All right. Now, this side, now I need to look up the other things that you can see on a data sheet. Is there's 2 things to an opto-isolator, the diode and the switch. In this case, the switch, in the MOC3021, the switch is a triac, which means it turns on in both current directions. So the only thing I care about as far as the switch goes is total current and voltage. So if I look on here, the detector, which in this case is the switch, off-state output terminal voltage, peak repetitive surge current is 1 amp. That should be fine, because all we're doing is switching the gate of another. So you can think of this as like a little pilot valve. It's using a small thing to switch a big thing. All right, so this needs to be under 1 amp. Let's see. And I will dictate that by the resistor. So we're going to take a line off of the main, and we're going to send it to the switch, and we're going to put a resistor in there to make sure the current is limited to 1 amp. Now I know that because I looked on the data sheet. All right, now the other part of the data sheet that I really care about is the emitter, or the diode. And that is a max of 3 volts and 60 milliamps. 3-volt drop. So I should be able to operate it with a 5 volts and a resistor to do the resistive drop. Because it's going to be on the back side. Yeah. I can compare that, actually. If I compare that to the 4N25, is that this one? I think that's this one. The 4N, yeah, the 4N25 input forward is 3 amps. Right. Oh, but it's 5 volts. So its limit is 5 volts. So this MOC 3021 is indeed smaller and more delicate. I need to make sure that it doesn't go over 3 volts and 60 milliamps. Is that emitter base breakdown voltage? Yeah. Yeah, input forward voltage. Oh, 1.5 volts. And reverse current. And then output collector, and we're dealing with, right. I think we'll be all right. So usually they say about a 220 ohm resistor for that on the control side. So I'm going to go ahead and, oh, nice. So we have a 200. That has never happened before in my life. Get the proper resistor right out the gate. All right, so what I'm going to do is I'm going to take this resistor, and I'm going to plug it into here, and here. Right. And then I can connect that to there. Is that making... Some breadboards are nicer than others. It doesn't always feel like they seat very well. Like you get cheaper breadboards, you end up wondering, like, is this actually making a connection? Okay, so that will turn that on. And let's see, what I can do is I can set up if I want to do a test program. No, I'm just going to create the whole thing. All right, so now I want to, oh yeah, pull up the data sheet on the BTA 08. All right, BTA 08. 08 data sheet. So again, all right, we got our data sheet right here. All right. Now the pinout of this here BTA 08. A2, A2, so A1, A2, and gate. Okay, so gate is the last one. So if I flip this around, yeah, that one really sticks in there. So if I flip this around, the gate is already done and hooked up. Perfect. Now, the gate, so it's gate and then anode 1, anode 2. And the reason it's A1 and A2 is because it's a triac, so it goes both ways. Kind of thing. Now I need to make sure what my gate, let's see. I am limited to 1 amp at 120 volts. Let's see, if I take 120 times 1.43, I get 171.6. And I want to make sure I only have 1 ohm, which means I need 171. Okay, it's current switched. Let's see what the max on current is for this. All right, RMS on state current value, circuit rate of rise on state, peak gate current. Peak gate current is 4 amps. Oh wait, I think this can only do 1 amp. I might need to find a different yeah, I might need to find a different symbol, emitter, continuous forward current. Oh, detector. Yeah, 1 amp. I think maybe I need to find a bigger isolator. Let's see if I have a bigger isolator. So I have an MOC 3063. Is that on here? Okay. Let's try the MOC 3063. OC 3063. MOC 3063 datasheet. Photocoupler. Yada 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 yada. Where's my specs? Input, output. 1 amp. Yes. Okay. We may be very limited. But If the rating is the same, why do I have multiples? Yeah, that's still 1 amp. Okay. Let's go back to the BTA, because whilst the max... So max gate is... Alright, parameter... And gate... Volt gate... BTA 08, volts, milliamps... Max... There should be a threshold. Here we go. So there's maps here. RMS on state current versus ambient temperature, max power dissipation, on state current versus temperature, and relative variation of thermal independence versus pulse duration. Most of those have to do with it is temperature dependent on the amount of current. So the more current it's passing, the hotter it gets. And the hotter it gets, it changes the current that it passes. Alright, repetitive surge peak on state, relative variation of critical rate decrease, on state characteristics. Let's see, that's that's amp, but that's not gate. Surge peak on state, relative variation of gate trigger current. Oh, changes per temperature. Okay. Thermal variation of critical rate decrease of main current versus junction temperature. Yeah. All right. I'm sure there's a number in here. Current gate equals 1.2 times IGT. Gate peak. Average gate power dissipation, storage junction, operating junction temperature, gate peak current, critical rate rise of on state times 2. Well, I'm not smart enough to know this. 5 to 50 milliamp. Triggering gate... sorry. Right at the beginning, I should have just read it. Triggering gate current is 5 to 50 milliamps. So it will trigger at 50 milliamps. And we're only doing 1 amp, so we should be good. Good enough to test, at least. Hi, Tom. How's you doings? Okay. 2. All right. Alright, so we have that hooked up to gate, and then this needs to be hooked up to power. You know what? Did I ever... I probably lost my, my jumpers. The jumpers I made for that power supply. I don't think I put them with the power supply. I may have lost the jumpers I made for that power supply. Because I am special. Well, such is life. What I can do is go here, power to power. So that powers that gate. And then I want a 1 kilo ohm resistor. What are these? 68 and 46. Oh, the 1K is gonna be difficult to find. How are you guys doing? I hope you're doing well. If I want my full 1 amp, I probably shouldn't use the 1K. Let's see, I would want to use something like 180 ohm resistor would equal 1 amp. And this thing is good for that, but this should work. Oh dear. Yeah, I almost goofed that up. I want this to go here, and then I'm going to take a resistor to there. So I'm going to take and split a resistor off to power. Yes. Right. So that means my current. So I have power coming in, and then the current. So power comes in, and then it goes through this resistor to the input of this triac, this opto-isolator, right? So that this then drives the gate of the triac through the resistor, and full power to anode 2 of the transistor, and then from there I can I had wires and they went missing. Oh, looking right at it. The jumper that I made for that. How about that? We can take this back. Since this is less than 1 amp, I was actually going to take the wires that I pulled off of this thing, but it looks like I may have misplaced them. Give me that. Do I need to make new wires? I may need to make new wires. This probably wouldn't happen if I organized things better. Of course not. Usaba. Usaba. Yes. I had wires. I lost wires. Because we're geniuses. To be fair, I didn't really think I was going to be using those wires originally, so I could have thrown them away. So I didn't think I was going to be using them. In fact, I can't use it. I can't use it anyways. I need to build more of this circuit in order to really put these things to use. I need to build the computer control portion of this circuit. But I'm still kind of bugged that I can't find those wires. It bugs me. I'll have to get over it. Maybe what I can do, I have this here manual version. How would I want to use that? How could I demonstrate that? So this item is pretty much exactly doing good. Glad it's Friday. Just joined in. Well, I'm glad you joined in, Tom. Your company is always welcome. As I'm kind of bumbling along trying to get this all figured out. Because I'm like, so this is the circuit. I want to drive it with the Arduino, but I need to program the Arduino. And the drawer of this toolbox is really getting under my skin. All right. So where are we as far as progress is made? We did the test on the heater element, and we figured out that it's less than 1 amp. So we figured out what pieces we want to use, and I'm a little hesitant about this here circuit being enough. A little hesitant about that. So I would love to try that. But in order to try that, I need to complete... Oh, wait, no. I could 100% operate that... Yeah, I could. I could 100% operate that manually. Put that there. This would go to positive. Yep. This would go to negative. Yep. That would turn that just on, which would be on. That would be fine. And then from there, I can drive. What do I want to drive? I could drive. If I really wanted to be frisky, I don't know if this wire is good enough to handle that amperage, but I could drive that heater and then measure on the oscilloscope. I could measure the power output. Yes. I 100% could. Yep. So if I did this on the oscilloscope, I could measure the power output. Yeah, and then the other one to neutral. So that would be to power. Yeah. And then the other one to neutral. I wouldn't have any control over it, but I could do that. Now I really wish I had those silly wires. Because I don't want to cut any more wires. Buggers. What about this? Like, we know this one's goofed. So, can I do this one? It needs neutral. What did I say this amperage was? We put full current, we put full voltage to this, and the amperage was 0.05, and this is a 1 amp, so this should be plenty. And, well, frankly, if this is plenty, then I don't know what I'm complaining about. Alright, so I'm gonna do some more redneck stuff. Because I guess that's just what I do. See if I can jam this thing in here. Right? And, of course I chose one that doesn't have a dual mount in. Dual mount? Yep. Alright. And then this goes over to here. Yes. Right, I need to change this to common. This needs to go back to common. Alright, so let's go with this one. This may not work that exceptionally well. I'm just not sure. Okay. That to there. And this lead needs to go to there. Ta-da! Okay. That should work. That should give us a test. All right, turn the scope on. Plug this in. Oh, I'm going to have to give it the 5 volts too. It's this thing right here. Wait, this isn't the thing. No! What is this? This is 12 volts. No! This is not the thing. I'm batting 1,000, guys. I am legitimately messing up. Come on. Where's my answer? This conundrum. Can I feed it? Nope. These are all too high. I need a 5 volts. That gives 20 volts here. Found the wire I was looking for. Oh, this bench. Oh, yay. Ran into a snag. Where's my... I don't have the power supply for my 5-volt reference. So prepared. So wonderfully prepared. All right, I can't go any further. Shucks. Yeah, if I put more than 5 volts on here, it's going to pass it through, and that's not good. I need to feed this with... Oh, wait a second. Done! We are resuscitated! Yay! Battery to the rescue. All right. Sweet. Now, scope. Lab scope. 4-channel lab scope. This should be good. Okay. That's plugged in. That wasn't supposed to happen. Dude, I think my circuit breaker just blew up. Yeah, I got nothing. Oh, I'm such a... No, it's right here. It's got a load. It has a load. Oh. That was unfortunate. I genuinely think I may have just killed this here circuit breaker. Because sparks came out of it, but it didn't trip. Yay. Alright. Let's try it out and see. Doo-doo-doo. And here, and just slip in there. Set this to voltage. Yep. My power supply went kaputs. Well, that's unfortunate. Well, at least it's on camera, I guess. Yeah, great. Now I gotta take this thing apart and find out what happened to it. Yay. Alright. I'm kind of running into the weeds at this point. So I'm gonna take this apart yet. And what can I do with that? Yeah, that's the gate. That's hooked up correctly. That's hooked up correctly. There's no reason. Nothing is shorted. There's no reason. Let's see what the inside looks like, I guess. That is disappointing to say the least. You get a circuit breaker because you're like, hey, you know. Supposed to protect the circuit, not just blow up. Supposed to be resettable. Yeah, there's kind of smells a little bit, but let's see. We have continuity. Nope, no continuity. Yep. The circuit breaker committed suicide. Go figure. Man, that is upsetting. Significantly so. It didn't even trip. The bloody thing didn't even trip. Uh, it's not the end of the world, believe it or not. I have another, a different. When I ordered this, I actually ordered two different versions. Oh, I think I just figured out why it went kapoof. It's only rated for 32 volts. So 110 volts was probably a little. We're just Yep, all right, my fault completely. That is not the appropriate circuit breaker for this circuit. So, I do have another circuit breaker. I'll have to find it. I think I put that one away. So I was like, oh, I don't need it. Yeah. I'll have to see if I can get this circuit breaker out of here. Because I kind of hot glued the thing in there and soldered it. And I'll have to rebuild that. Whatever. Okay. Alright, so what I'm going to do at this point is I'm going to go back to the drawing board. The circuit simulator. I'm going to play around so that I can put these components in. And now that I know my voltage and amperages and limitations, I can actually figure out, I can size the resistors and everything to operate accordingly. That is something that the circuit simulator does pretty well. Okay, so that's what I'm going to do. I'm going to go back to the drawing board. Not the drawing, I keep saying that. I'm going to go back to the simulator now that I know my ratings, and I'm going to construct a circuit for this based on that. So the steps are to, like, this is such a simple circuit. It really doesn't need to be anything more than this. However, I'm going to be doing something something else that I've never done before. Like, get this. You guys want to see what's crazy? This entire circuit already does what that entire circuit does. So for all these components here, all these components, just these two get the job done. Doing the same thing. Yeah. Anyways, that's why we're using Triax. So, I'm going to design this up a little better. And, oh, what I was talking about. So these here gadgets, these are, I haven't even opened the bag yet, but these are, come on, hard to get to, is what they are. They're hard to get to. There we go. These are what's called 80 tiny chips. And these specifically, there's several versions. So these specifically are the 80 tiny 85. And what that means is, this here chip, this one right here, in my hand, that chip is a mini computer. It is a microcontroller. It's crazy, I know, but I can program this. I can program this chip very similar to the one I can this chip. It doesn't have, obviously, it doesn't have nearly as many inputs and outputs. But it does, indeed. It is reprogrammable. And it will perform the function of driving this circuit. It'll perform the function of the driver that I need. In other words, it can take an input, a PWM input from another controller. So it can talk to a different controller and say, hey, I only need 50%, or I only need 75%. And it can interpret that signal and then drive this chip using the input from this, right? So this is going to feed a signal into here. This is going to feed a signal into here. And then I'm probably going to have one more signal fed into here, like a start-stop command kind of thing. And then it will drive this. That's what we're doing. So that's going to be fun. So that's the second step. Or I guess the second next step. So I'm going to go to the circuit simulator and make sure all my resistances are good. Then we're going to work on programming this chip to do the driving operation. And once I'm confident that all that should work correctly, then we'll put that on a proto board. I really don't need this. I don't need a proto board this big, but it's what I have, so that's probably what I'll use. So we're gonna put this with this on a proto board, and make its own little daughter board. And at the end of the day, this Arduino is going to take input signals from a potentiometer right here. So it's going to take input signals from a potentiometer and from a temperature sensor right here. So this here temperature sensor will feed the Arduino, and the potentiometer will feed into the Arduino. Then the Arduino is going to print out the information I just had right here. It's going to print out the information on this screen. It's going to say temperature, which is going to be the plate temperature. And then it's going to say set point, which is going to be settable by the potentiometer. When we turn that, it'll change the set point. And then it's going to say power percentage, which is going to be how much this is telling this chip to run. So these, so far, are the components that we're going to use to drive this. that's the plan. So as soon as I can confirm that, program that, put it on its own little proto board, start putting things. You know what? I'm gonna save a point for this on that proto board too, because that literally just needs to be an input and output, so that can just be a separate plug. Yeah, and there we go. All right, so I'm gonna cut it off here. And what are we at? How much time are we at? I don't even know. So I'm gonna cut the live stream off here, and I'm gonna post the live stream that I recorded over to the YouTubes, and I'm going to keep working on this. So when we come back the next live stream, hopefully we're going to be putting all this onto the proto board, like building the next. So this is a proto board, right? So we're going to be building the next proto board, and actually hooking up. That stuff all over my socks, and actually starting to hook up power, and we'll have it sitting out like this for temporary. To be able to power once we know that it all works, then we'll be able to power it on, do the oscilloscope testing, see if we need any snubber circuits or anything for that. But get a feel for it once we got a feel for it in pieces. So yeah, when we come back, we're going to be building this stuff. And if I do my job right, we're going to be building this stuff and actually assembling it in a manner that puts together. Maybe I'll go over the programming. I might do another live stream specifically for the programming of this chip, as well as the programming of the Arduino Nano. In case you're wondering why I want two microcontrollers, the controller that needs to operate this chip needs to use an interrupt signal that runs off of, that's what this zero cross is for. When it does that, it slows the computer down. I don't want to have a slow computer. So I want these two things are going to run at two different speeds, is what it amounts to. And I want them to be able to do that easily. All right. Yeah. Next time, building, then another one for programming, and then another one for actually testing, and then another one for putting it all together, assuming it all works correctly. Sweet. Thank you very much for watching, everybody. I really appreciate it. And I'll see you on the next stream. Let me know if anybody prefers the Facebook. It didn't really seem to make much of a difference on views. So it really doesn't seem to make much of a difference whether it's on Facebook or on YouTube, apparently. So, yeah, we'll see how the video performs on the YouTubes, I guess. Thank you very much, everybody. Have a good night. Until the next time.